Okay, so good afternoon, everyone. Welcome to this edition of the NITheP and NITheCS colloquium. As you know, we are in the process of transitioning NITheP to NITheCS, but we don't have yet an official NITheCS logo. So we will hopefully have one very soon. Yeah. So it is a pleasure this afternoon to have with us Dr. Aniekan Ukpong. Aniekan studied physics in Nigeria, where he graduated with a BSc honors in physics from the University of Calabar in 1997. And he completed an MTech degree in solid-state physics a few years later at the Federal University of Technology in Akure. From there, he moved to the University of Cape Town, where he graduated with a PhD in 2008. Yeah. After his graduation, he had a few postdoctoral positions. One first at the University of the Witwatersrand, followed by one at University of Pretoria. And since 2014, if I'm correct, he's been with us at UKZN on the Pietermaritzburg campus, and I think as a senior lecturer from the very beginning. Yeah. So Aniekan, it's very good to have you here. And you know, NITheP will have in future a C and S in the name. So the title of your talk is just perfect for our new computational sciences in our institute. Yeah. And sorry, with us today is also Professor Ilya Sinaisky, that most of you know because he's the canonical co-host of this event. And he, as usual, kindly agrees to moderate the questions at the end of the session. So please, if you have questions during the talk, make use of the Q&A facility, or since we are not too many, raise your hand and we will make a plan to give you the permission to speak. So Aniekan, people are here to listen to your talk, not to listen to my introduction. So you're welcome to share your screen and start with your presentation. So thank you very much, Aniekan.
Thank you very much.
Green button.
Yeah, I've done that.
Okay, then you just need to find your keynote or PowerPoint or whatever you're using. Okay.
Can you confirm that you're able to see what I'm sharing, please?
Yes, if you put it on full screen, it will be even better.
Okay.
Maybe you need to click on the presentation mode because we can still see all the I think it's the Adobe Acrobat Reader that you use, yeah?
All right, what I was sharing was the PDF version.
No, click on full screen, Control L should do the trick.
No. I did Control L, I did Control Shift F5, but it didn't do that. I think it's fine now, right?
Yeah, now it's just fine. Yeah, perfect. So now we are
perfect. Thank you very much, Francesco and Ilya and the team for setting this up. It's really a pleasure to be able to address you today on the occasion of this NITheP Colloquium. As you're probably aware, the title of the talk is going to be High Performance Computing Insights from Condensed Matter Materials Physics. And just to rectify what Francesco said in the intro, I only joined the UKZN on the 1st of October 2016. I thought I heard him say 2014. That's not correct. All right, so pardon me then. Before I start, I'd like to acknowledge the support of a couple of institutions that I consider as strategic partners in my work, and this includes my host university, the UKZN, the National Research Foundation, the Center for High Performance Computing, and of course, the most recent crown in the jewel, NITheP. So it's really an honor to be able to address you today. All right, so my talk is going to follow this outline. And shortly after this introduction, I'll share with you what has motivated the work that is done in my research group. In fact, I will share with you what constitutes the main motivations behind my scientific endeavors in physics. I will discuss with you materials modeling tools that I routinely use, and I will share with you the quantum mechanical basis for doing my scientific computing in condensed matter systems. And that will lead me naturally then to introduce you to the quantum theory of solids and describe the essential underpinning theory of the computations we do, which is the Kohn-Sham ansatz of density functional theory. And then I will share with you selected highlights from some of my scientific computing projects that are mainly based on high performance computing. And then in the course of all of this, I will be highlighting to you in violet colored text within this presentation, areas that I believe that we could work together with people who are already well established within the NITheP or NITheCS framework. So I will give you an outlook which essentially encompasses paradigms that have started to emerge within the scientific computing research space. And lastly, I'll conclude with a very personal viewpoint on how things should be done in physics. All right, so this is what my research group looks like at the moment. We are technically having 6 PhDs and 1 MSc to work with, distributed between the University of KwaZulu-Natal and the University of Cape Town. And of course, there is one principal investigator, which is at the moment myself, but you could imagine that I am really, really interested in seeing if I could foster new collaborations within the NITheP, NITheCS context. All right, so our computing is mainly done under the principal investigator initiative of the Center for High Performance Computing, where I run the MA8SO941 research program. And that program is also supported by the NRF grant. Not long ago, in 2017, I got the CHPC to support my computational teaching and research program at the UKZN with our HPC ecosystems, within the HPC ecosystems project, where they donated for us a set of compute nodes that are managed on our behalf by the Department of Computer Sciences at the UKZN here. So our overall goal really is to do physics using condensed matter systems as the platform. So you could imagine then that we are really motivated by the things that we can use the theories of physics to be able to compute within what you could call condensed matter systems, basically a macroscopic solid that contains very many degrees of freedoms, ranging from ionic cores, that's many atoms and many electrons. We like to test the theories of physics from the point of view of, first of all, computing the ground state properties that I've listed there. And I'm particularly also interested in the linear response properties of condensed matter systems and the carrier transport signatures. You will see when I'm sharing with you the highlights, the scientific highlights of my research, that a lot of the things I do actually start from, first of all, determining the global ground state property of my system. It doesn't matter what the local structure looks like. And from there, I try as much as possible to study what the linear response of that system will be by considering things like effects of symmetry breaking fields, like application of an external electric or magnetic field, things like spin orbit coupling, maybe doping, maybe application of strain gradients or pressure gradients, that kind of thing. I'm also interested in understanding the effect of intrinsic broken spatial inversion symmetry on the electronic ground state. And in that case, I find it particularly fascinating to study systems that have heterobilayer or multi-layer interfaces, systems that allow for compositional degree of freedom to be changed. And I can tell you that there's a lot of interesting physics to be discovered, because things start happening when you subject your global ground state to fluctuating degrees of freedom, which quite frankly may or may not necessarily be accessible experimentally. And that is why for me, the computations I do are more guided by what quantum mechanics allows me to do within the context of density functional theory than what the experimentalists have been able to figure out themselves, except they ask for very specific questions that I consider reasonably enough to devote my computing time to. So I'm also interested in principle to use quantum mechanics to describe ab initio thermodynamics. And that allows us sometimes to wander into the world of thermochemistry and reaction thermodynamics. All right, so part of the things I'm doing at the moment involve spin tunneling spectroscopy, defect fingerprinting, as you'll soon see. And I can safely say that what research institutions spend millions of dollars to achieve, we can achieve using HPC computing. For example, we can compute electron paramagnetic resonance signals of any arbitrary condensed matter system. Similarly, we can do that for the electron spin resonance structure. We can do both charge and spin tunneling, and we can go as far as computing spectroscopic signatures of defect states. And I dare say that I am hoping that at some point we could be able to find a common ground where that kind of capability could be deployed for quantum braiding statistics that is relevant in quantum computing. We can also do exotic type of spectroscopies like the point contact Andreev spectroscopy purely from a computational perspective. And that allows us to, for example, track the electronic signatures of Majorana zero modes and do an inverse mapping to study the semiconducting gap in model superconductor materials. We can do a computation of spin tunneling spectra, and we can also compute the Hanley effect. All right. So to understand what motivates me from the point of view of materials, we need to realize that from my perspective, condensed matter physics is nothing other than, in fact, condensed matter theory is nothing other than applied quantum mechanics. So one of my key objectives is to understand quantum materials from the point of view of quantum mechanics. And that usually means the adoption of the first principles approach to perform density functional type calculations. All right, so my goal too is to access the quantum state of carriers, and that those carriers could be charge carriers, it could also be spin carriers. So we could computationally then track the signatures, the electronic signature of charge carriers and of spin carriers. In other words, we can invert spin, separate them, and completely track the signal of spin up and spin down electrons if we're interested, and we can break the symmetry of spin coupled systems by applying symmetry breaking spin orbit interaction. I'm sure you know that when spin orbit interaction is applied to electron states, that degeneracy of electron states are completely lifted. All right, so here is a typical fascinating crystal structure of a compound that is made up of arsenic, iron, and sodium. You will see that by making very slight changes to the composition of this material can undergo very interesting transformations that can take it from a mundane magnetic behavior to a superconducting behavior. So finding out how composition variations dictate the structure, and also understanding the nature of the fundamental interactions between the constituent particles in the material and the observed physical properties, such as in this particular material requires a wide range of experimental and theoretical techniques. And for this particular material, you will see that through HPC, one could achieve a lot, cut costs, access the physics that are otherwise intractable using conventional methods of scientific inquiry. So overall, you should understand that the goal of what I try to do here, or what I'm trying to do here at the University of KwaZulu-Natal under NITheP, is to explore paradigms that typically enable our use of the computer as a one-stop laboratory for scientific research. All right, so here in this slide, I'm going to share with you what I consider to be my motivation for doing what I do from the point of view of technology. All right. Sorry, from the point of view of materials. So from the point of view of the material. Sorry, I can't see my header file because of, all right, now I can see. You would imagine then that condensed matter physics has been around for a very long time. In fact, the American Physical Society reports that at least 70% of all physicists in the United States claim to be condensed matter physicists. So you imagine then that globally a lot of work has been done in this field. Then it becomes a big challenge to contribute to a field such as the one I'm engaged in. But within that, there's still some very fascinating physics to be discovered. For example, in 2015, Liv and his group found out that in a material called tantalum arsenide, bulk tantalum arsenide, whose crystal structure I show there, the inherent lack of structural inversion symmetry allows a very exotic kind of physics to be studied. For example, you remember that the 2016 Nobel Prize went to physicists who studied topology. Now, that whole concept of topology in mathematics left the maths department, entered the theoretical physics domain, and now we are routinely doing topological physics using tantalum arsenide as inspiration. Now, to understand then, remember that a couple of years prior to 2016, people were like fascinated about what can be done with graphene. And graphene had that magic Dirac point, Dirac cones that appeared invariant at the time invariant symmetry points of the Brillouin zone. Now here is tantalum arsenide, a material that lacks structural inversion symmetry, but now with two closely spaced Dirac-like cones, and the surface electronic structure at the middle, they host what is understood as the well node. Those well nodes are typically collective excitation modes that can be tuned to become a carrier transport phase in typical applications. So those are the kind of things that attract me. On the other hand, here you have Van der Waals heterostructures. Now you could imagine then that a Van der Waals heterostructure is just some designer material that can never be formed through your normal physical vapor deposition or any other wet chemistry kind of technique. But these are materials that are designed layer by layer. So you typically would grow one layer using some method and then physically lift them and stack them to form a Van der Waals heterostructure. And this layer is stable thermodynamically, and they are coupled together exclusively by Van der Waals interactions. All right, so for some years now, I've been exploring this kind of material. For example, in this case, you could stack at the bottom there some transition metal dichalcogenide and put in something like graphene and stack them like that and put a tunnel barrier material with a wide band gap. Now, ideally, if you do that physically in the laboratory, you will need to win some magic grant to succeed in doing this. But with just a laptop and access to the internet and HPC resources, we can access the same physics. When I say the same physics, is whatever we compute is able to be discussed in the global arena and argued with international level scientists in physics. All right, another material that attracts me is this kind of multi-layer heterostructure. You could imagine here, this is a bilayer system of tungsten diselenide and molybdenum diselenide. However, if you decouple them individually, each of those layers, their electronic signatures are completely different from the electronic signature you would get should you stack them. Now, the interesting thing here that I want to draw your attention to is the fact that by the time you do a more rotation of this lattice, for example, you rotate the overlayer with respect to the underlayer substrate, you see a totally new lattice structure that forms that hexagonal pattern. That pattern is a Moore phase. The electronic structure of the Moore phase, when compared to the electronic structure of the unrotated heterobilayer, are totally different things. They give you different physics, different electronic signatures, different carrier transport properties, and we are able to explore the rich physics associated with that kind of system. So then you would imagine that for a typically mundane bulk material like bismuth selenide, which is inherently topological, we have direct access to the topological physics of the material because, for example, here you could see that computationally one can tune the electronic structure from a point where there's only one Dirac cone. See the top Dirac cone separated by a band gap region and the cone in the valence band region to a point where it actually starts hosting two Dirac cones. The carrier properties at that electronic phase will never be the same as that of the one here, simply because of the symmetry breaking fields that must have been applied to the ground state electronic structure there. All right, lastly, I'm interested in what the laws of quantum mechanics allows me to do within the context of Landau level filling. Everybody knows the first quantization rule of quantum mechanics, where energy levels are quantized according to n plus half h bar omega. All right, now the Landau quantization in condensed matter systems like this shows clearly a concept that otherwise you will only hear in a typical theoretical physics class. But now we can routinely use the computer to gain access to this. So each of these discrete lines you see here denote a discrete Landau level, which is very familiar to theoretical physicists, especially to quantum field theorists. All right, so here is the technological basis of our HPC projects. Magnetic tunnel junctions, as you could see, is a very important component of the spin transfer torque memory devices, including the voltage controlled magnetic random access memory systems. Now, the magnetic tunnel junction is this unit here that has the green layer separated from the blue layer. The green layer basically is a magnetic material whose magnetic moments have been allowed to be free. In other words, they only respond to the applied symmetry breaking field, whereas the reference layer magnetization is typically controlled. It's fixed. That's why it's called the reference layer. The tunnel barrier region is what it is, an insulating region, or at best a semiconducting region. Now, being able to control the flow of carriers, whether charge carrier or spin carriers in the case of spintronics, will allow one to develop technologies for reading and writing of information. Now, this inspires me a lot because from the previous section, you could see that purely from the point of view of physics, we could stack materials of any kind, of any crystal structure, and investigate the new signatures we could get to a purely technologically driven material that looks like this. This is a very complex material that can never be formed by conventional deposition means, but these are stacked materials. But computationally, we can investigate this using the Van der Waals heterostructure architecture. And you could see then that the magnetic tunnel junction plays a supercritical role in this kind of integrated circuit that is typically found in modern day memory systems. All right, the latest, which just came up this year, this paper just came up this year, is a scenario where the magnetic tunnel junction architecture has been combined with the same Van der Waals multi-layer heterostructure to couple spintronics to solar photovoltaics. So this kind of emergent technological systems serve as a big motivation for the research I do. All right, so in this case, photo-generated hot carriers can be harnessed in spatially confined photovoltaic materials, which are essentially made up of 2D Van der Waals heterostructures, systematically stacked one on top of the other. And the reason for that is due to the slow hot carrier cooling and restricted loss channels that result, that could eventually result in improved power conversion efficiencies far exceeding the Shockley-Queisser limit. All right, so now, as you would imagine then, the work we do in our group typically targets a multi-scale, multi-physics modeling philosophy, simply because if you restrict yourself to the fundamental limit too much, then it seems to lose touch with what is going on in the global technological space. But if you stay there in the global technological space for too long, then you lose contact with what is going on in the theoretical physics laboratory, for example. So I try as much as possible to work within tools and frameworks that allow me to remain relevant within that spectrum. So here in this graph is just a diagrammatic plot that encapsulates the kind of computational paradigms that we adopt, where on the time axis, we are displaying the time limit in which we can gain access to materials properties, whereas on the length, on the horizontal axis, we are plotting the length scale on which we can gain access to material properties. For example, ab initio methods will typically be dealing with in the femtosecond region and in the angstrom region, but when you go to the continuum limits, then you're becoming more relevant to what is typically in the applied physics domain. So, and part of what I do to build on my previous experiences working in the private sector, where you try to always link the science to the application. So that has driven what I do. All right, so here are the tools that we are using at the moment. You could see we are not tied to any particular thing. There are so many different things going on, but our workhorse is high performance computing, and we are gracious to the, rather we are graciously supported by the CHPC through their provision of the Lengao supercomputing capability to us. And we are able to do that through open source computing. You could see that our primary coding platforms and mathematical software libraries span Fortran to Python, but we have a capability to also do things in C and C++ too. At the moment, I am deliberately looking for collaborations within this new emerging areas of interest. I am open to things in big data. That's why you will see me feature in the recent big data school facilitated by NITheP, where, for example, there's a project currently in the group where we are starting a coarse graining of the ground state electronic structure and using it as an input to the Landau, Lifshitz, Gilbert, Slonkowski type Ising-based model to form a spin ice-like model for tracking the time evolution of spin. And I will show you in the scientific highlights where we are actually using it to blow Skimion bubbles. All right, so I'm also interested in the kind of things that are possible within the domain of machine learning, where computing within the NetKit and the scikit-learn platforms have become particularly attractive. But my routine research is based on electronic structure and atomic scale calculations. And the interfaces we use include the atomic scale environment developed by physicists at the University of Oslo and a team in Technical University Denmark. And then for visualizers, we use the XCRISDEN, which is developed by Anthony Koljaj from Czech Republic. And we are also flexible. We can compute in Python. We use Matplotlib as the plotting utility. We can do both periodic and aperiodic DFT using those codes available, listed there. And sometime last year, I delved into semi-empirical tight binding models as implemented within the code I wrote when I was doing my PhD at UCT and porting it to PAO Flow. PAO Flow is written by a couple of people in Denmark too, but not at the technical university, but I think the university in Lyngby, if I'm not wrong. All right, so that's the tool set that we use. All right, now let me give you the theoretical basis of our project. And that is, strictly speaking, the quantum theory of solids, quantum theory of the macroscopic solid, where, as you would imagine, our condensed matter system, whether it is a single phase or multiple phase or single layer or multi-layer electronic gas system, can be described using the time-independent Schrödinger equation. That is the idea, the fundamental idea. But as you probably know, this problem as it stands is numerically intractable. Computationally, we are nowhere near solving it. So if we were to, in principle, construct the many-body Hamiltonian for this, then that would be the kinetic energy. This would be the correlation energy due to the Coulombic interaction of the electron with one another. Of course, there is electron-electron repulsion. And then this will be the potential, the Coulomb potential due to the Bay ion potential as they're interacting with the electrons. But fortunately for us, we can utilize the Born-Oppenheimer approximation, which is essentially an assumption that is firmly rooted in molecular physics, that the electronic wave function depends on the nuclear positions, but not on their velocities. That is, the nuclear motion is much slower than the electronic motion, to such an extent that the nuclei in a macroscopic solid can be considered to be at rest. To that extent, the nuclear motion, that is, the rotation and vibration, only sees a smeared out potential that is set up by all the mobile electrons. That is a big help. That assumption is a big help for us from the point of view of solving this time-independent Schrödinger equation for a macroscopic solid. However, the analytical solution of that many-body Schrödinger equation is quite frankly not possible. And the numerical solution, while in principle perfectly realizable theoretically, is effectively impossible to achieve in practice for systems that contain a significant number of electrons due to the finite speed of the computing systems we have and the memory of computers. All right, so now there enters the Hohenberg-Kohn theorem that offers us a framework for escaping that dilemma. The first theorem of Hohenberg and Kohn states that, I'm sure a lot of you will already know this, but for the benefit of those who don't know, the theorem states that the ground state energy of a system of electrons is a unique functional of the electron density at ground state. So then that if we are able to find the total energy of our ground state, in a macroscopic system, then the functional that allows us to do that represents the functional of the global ground state. All right, the second theorem states then that the true ground state density for an external potential, remember then that in the context of the statement of problem that I just made you understand, you see that our material could be subjected to external potentials that are essentially symmetry breaking to the global ground state. So we want to know how to formulate the time-independent Schrödinger equation to accommodate an externally applied potential on top of the potentials that appeared in the many-body Hamiltonian that I described previously. So then, theorem 2 of the Hohenberg-Kohn theorem says then that the true ground state density for an external potential is the density that minimizes the energy of the variational ground state. Thus, the challenge then is to find that universal functional of the density. And the universal functional of the density then becomes the minimum internal electronic energy of any electronic wave function or ground state or otherwise, whose corresponding density must be equal to this iterative minimization relationship. All right, so I would then like to comment that all the densities that integrate to the total number of electrons, n, in the system, corresponds then to some n electron wave function. And this property is typically understood in the condensed matter theory domain as the n representability of the electronic structure. This then effectively avails us with the framework where we can do DFT in practice, but there are consequences to that n representability. And the first one is that you need to be aware of the fact that at this stage, we are still nowhere near to a practical method of solving the macroscopic many-body problem, because the exact evaluation of the universal functional will require us to solve the same old many-body Schrödinger equation that we're trying to dodge. However, and here is where the Kohn-Sham ansatz of DFT comes in. And so to understand what that ansatz is actually doing, suppose we have a functional that we could say is a good approximation of the universal functional of the ground state density. Then it can be evaluated in a practical manner in such a way that any search should lead us to a good approximation of the ground state energy and density. That is the principle. And that principle is the fundamental basis upon which all practical density functional calculations are founded. The proviso, though, is that we are still nowhere near to solving it. And this is where Kohn and Sham won their Nobel Prize when they did, because they recognized that as far as succeeding in computational condensed matter physics is concerned, if you do not like the answer you are getting, then simply change the research question. And what they did then was to effectively replace that difficult problem of the macroscopic many-body problem with an ansatz that is essentially based on a fictitious or auxiliary system, such that the auxiliary system obeys the same Hamiltonian. However, the Hamiltonian can be solved rather easily. For example, so this is an interacting many-body system. The Kohn-Sham ansatz transforms this many-body interacting system into a non-interacting many-body system where each of the red balls in the, or each of the particles, the electrons in the non-interacting system are seeing a uniform potential. That is the key there. So the ansatz assumes that the ground state density of the original interacting system is essentially the same as that of a chosen auxiliary system of non-interacting particles. And that is the idea of non-interacting representability. So there is our n-body Schrödinger equation written out in exact form. And they are the same equation for the same system, but transformed such that they are now seeing only this Kohn-Sham potential, this term in the red box. So then the electron density of the exact system is then computationally, or at least numerically, exactly equal to the DFT density. That is the goal of the Kohn-Sham ansatz. All right, the particles then will have to move in our fictitious external potential. The challenge is we don't know what that potential is. In fact, that potential hides a lot of our ignorance about our system, because every other term in that Hamiltonian is essentially known. The only thing we don't know is the contribution to that, basically the expectation value of that Kohn-Sham potential. If that Kohn-Sham potential were to contribute a term to the Hamiltonian of the ground state, then we don't know its expectation value accurately. And I can tell you that a lot of work spanning more than 40 years has gone into developing functionals that allow us to track the exact nature of that exchange correlation contribution to the total energy. However, I want to note that although there is no proof that there is an essential truth of the Kohn-Sham framework for all ground state densities, there is no example till this moment that proves that that truth doesn't hold. And the community generally assumes that the assumption that a reasonably good approximation of the exchange correlation energy contribution, when made within a generally acceptable framework, is good enough. All right, so the exchange correlation energy functional and its derivative, which gives us the potential, can both be expressed as a sum of terms. So you can call it the exchange correlation energy due to the electrons interacting with one another, because electrons, when they come close to the other, must experience a repulsion, a Coulombic repulsion. And there has to be a kinetic energy part. So essentially the goal is to find a functional that represents that interaction by differentiating the expectation value of the exchange correlation contribution to the total energy with respect to the density. And we can also partition it into two terms. The quantum mechanical exchange correlation correlation energy, XP, and the Pauli Coulomb component of the potential can thus be expressed in terms of field E, which, as you could see, this is nothing other than the Coulomb type of potential. But getting its exact form is not a trivial challenge, right? All right, so there's a lot that goes into practical DFT within the Kohn-Sham framework, but I want to say that the correlation energy always has to be approximated, and people have spent a lot of their time developing functionals that do that. For example, here is a ladder called, this ladder was proposed by Jacob Perdue, who is one of the pioneers in the development of functionals that match exactly what I described to you. And in this ladder, you could imagine the higher we go up, the better the chemical accuracy. And the lower we go, the simpler the nature of the functional. So part of the goals of practical DFT is to do performance testing of the zoo of density functionals that are currently available and accessible to the community. However, mapping the electron density to exchange correlation potential has been so far established accurately for semi-local, within the semi-local approximation and within the gradient corrected approximation. The semi-local approximation was done by John Perdue and Alex Zunga many years ago, and Perdue, Bock, and Enzerhoff have introduced the generalized gradient approximation with or without some non-local augmentation of the Hartree-Fock exchange and applying linear response theory to it. Nevertheless, the challenge from a computational perspective is to achieve a balance between chemical accuracy and computational tractability. All right, so for example, here is another area where there could be some scope for collaboration with NITheP partners or NITheCS partners, where, for example, this year, a team coming out of physics at Cambridge just did an iterative minimization study of this relationship to within the linear response time-dependent density functional theory to calculate the exact exchange correlation kernel, and they plotted this nice-looking correlation. You could see that the goal is to hit this sweet spot where there's a linear correlation, but look at the deviations they are getting. But that's good enough for publication in the Physical Review B. And computing paradigms such as machine learning, big data, orbital free DFT, and materials informatics, as you already know, have emerged. So my goal then is to see if I can partner with some of you in audience, if your interest fits it, to develop machine-learned exchange correlation functionals using either trained neural networks, supervised ones or unsupervised artificial neural networks to do this. Others have done it, so I don't see why we can't do it. All right. Now, before I leave and start showing you my scientific highlights, all functionals are essentially approximations. Any way where you read that DFT has failed is actually a report of the failure of the exchange correlation functional. Density functional theory is an exact theory, it's an exact quantum mechanical theory of the global ground state, so it can't fail theoretically. No functional is accurate for all properties. No matter what functional is invented, whether it's machine learned or what, someone somewhere will always find a case where that functional fails. And any functional can be applied to any electronic structure problem. In this sense, it is ab initio, but we use experience and intuition to decide which one. All right, so here is the quantum mechanical basis of our current projects. It's important that I give you this framework so you understand exactly what I'm going to share with you from the point of view of our scientific highlights. That is that our global ground state density, total energy as a function of the global ground state density, it is expressed as a function of contributions. That is the external potential, that is the Coulombic interaction, that is our kinetic energy, and that's that term that hides all our ignorance that I said computationally we have to find our best approximation for. Now, I have been interested in evaluating the topological classification of electronic phases and their spin textures. So the idea then is to use DFT or quantum mechanics to determine the ground state and use more approximate theories based on tight binding models to determine their topological classification. And to do that, I map my global ground state into some time-independent, or rather time-dependent Hamiltonian. Time-dependent because TNN on the artificial lattice will then be the ground state. This term becomes a sum of symmetry breaking fields that I choose to add. For example, I can introduce the intrinsic spin orbit interaction. I can introduce the Rashba term for systems that have surfaces or interfaces. And I can then create an additional term that allows me to penalize the absence of spin inversion. So this model allows me then to transform my tight binding model into an Ising-like spin space Hamiltonian, where all the information we got here from lower level theories are fine-grained on the Ising model. And we only really worry about the Heisenberg coupling and the Bialoshinsky-Moriya interaction term, where S is our spin vector per lattice. All right, so I think that has given you sufficient background theory. Here then are the scientific highlights of what I've been doing. The first thing is that we've just recently discovered through computation that there is dynamic exchange bias in that kind of system when you employ computationally the spin Hall effect geometry in spin Hall effect geometry to compute the injection of spin from a ferromagnetic contact through a tunnel barrier region into an otherwise non-metal, such as platinum. So you could see then that the hysteresis loop here, which have blown up here, kind of reflects a weak magnetic state. That when we inject spin current in the forward bias and in the reverse bias, we dynamically create a hard ferromagnetic state denoted here. And that allows us to blow skimion bubbles. So we technically have found that computationally you could dynamically create metamagnetic transitions from the soft to hard ferromagnetic state during spin Hall effect, and that allows you to blow skimion bubbles. Now, what do I mean by that? So I'm sure you know Tom Skene. It's a British physicist who many years ago developed a theoretical construct known now in condensed matter physics and in theoretical physics, in fact, as the skimion. The skimion is a collective mode for exotic particles. Here is our skimion that we've created recently. You could see that I've used this to demonstrate recently an electrical read-in and electrical write-in and read-out signal using this skimion bubble. So the idea then, from point of view of application, is to encode information to the skimions where 1 will be coded there and 0 will be coded there. And you could see that the dynamic exchange bias really does not really change the magnetic state, because during the right stage, shown in this lower plot, the magnetization state remains fairly constant, where this transient region denotes the region where you shift from forward to negative bias. All right, here is our demonstration of possibility of magnetic data storage without the need for spin transfer torque. So I am proposing then that dynamically switchable magnetic quantum bits could be pursued as a hardware platform for realizing quantum computation for those that are interested within the UKZN. And then I'm also recently involved in using quantum mechanics to explore the near field quantum electrodynamics of quantum phases in condensed matter systems, where we basically solve the time evolution of the Schrödinger equation in the projector augmented wave framework and expand the basis sets using linear combination of atomic orbitals. So this is the numerical representation of this Hamiltonian, and this is the leapfrog algorithm for evolving the Hamiltonian with time. Now, you look at the local field enhancement and the induced field enhancement, and this also led us to predict the emergence of topological order in the transport phase using topological invariant. So on the left, we have topological phase diagrams. On the right, we have the equivalent band structure with their topological index, where 0 denotes a trivial phase and non-zero, this pair of numbers denote the topological invariant number, Z2, and the chain number. So, for example, 0, 0 will denote a trivial phase of the same material, but 0, 2 and 1, 2 and 1, and 1, 2, this is a repetition, ignore it, denote a non-trivial phase. And what I mean there is carrier transport in non-trivial phases are not subject to external perturbation. So we've also, within the same framework, illustrated the signature of carrier density wave state set up at distinct topological phase transition points discovered in those two systems. And these energies denote unique energies at which the topological phase transition occurs. So you could see that within a graphene nanoline, we are setting up a standing wave mode where blue denotes a minima, red denotes a maxima. You could see, depending on the phase transition point, the wave mode changes. Now, my proposition is that the typical Lindblad master equation that is needed is required to be solved for quantum control and quantum information processing can be solved using the same framework, and in particular, realizing that for quantum control of two interacting quantum particles, the representation of a coherent state, thermal state, or Fock state, using, for example, the quantum harmonic oscillator mode representation of the Hamiltonian, contains very little information. Because, for example, in quantum mechanics, the probability distribution plays an important role, actually does not tell us the full story about the expectation values that you compute from your probability distribution. So my question is, can the induced field mode that I shared with you earlier for graphene or for any other structure in particular be used as a mapping of the Fock state or the thermal state or even the coherent state that you would use in quantum control if we were to make condensed matter theory to be relevant in what you do? All right, here is work that has been published. The ones I shared with you aren't published yet. So this work basically shows that at the ground state, we can demonstrate Handler spin splitting. Unfortunately, I have to be rushing now. So you see, we split the electron chair, please. My time is up. I can stop, but I still have a couple of slides to share with you, but with your permission only. Otherwise, I am ready to take comments.
Go ahead, Aniekan. Just we still have a few minutes. Don't worry. Yeah.
Thank you. Thanks a lot. All right. So here is the stack geometry. The top layer in this case is made to represent a magnetic tunnel junction simply because of the technological motivation of my work. Now look at what happens at the electronic density of states. We notice that at the energy reference, which denotes my Fermi level, there is a spin splitting. So this is something that was initially discovered in the astrophysics community. This Hanley effect was first reported in astronomical spectroscopy, but here we are realizing it in a condensed matter system where after decomposing the electron transmission or the spin transmission spectrum into spin up and spin down, you could see clearly that the Fermi surface topology looks differently. The spin up and the spin down channel have different conducting channels. The Fermi level topology has far fewer conducting channels there than here at zero external electric field. And an application of an external field that filters the spin allows us to clearly transmit spin up in this case and spin down in that case. And this work was good enough for PRB. And we demonstrated that that kind of architecture can be used to store information. Basically, there is a perpendicular magnetic and isotropy, wherein information stored at that state is maximal and it vanishes at that state. And application of an external field showed us that there is a first order response between the PMA and the applied electric field, in that it initially tends to increase in region 1, reaches a critical field, saturates, and starts dropping. All right, so we track the response of the local structure to the applied field, where A, B, C, and D represent slowly progressing intensities, progressive increase in the intensity of the applied field. This is the zero field case. Of course, you can see that at high electric field, the number of conducting channels in that spin up and spin down channel become significantly reduced. Here is another work that we did in the past, good enough for Journal of Physics D, an IOP journal. Here we demonstrated the sensitivity of the tunneling spin conductance to the material platform, where we demonstrated control of the tunneling magnetoresistance. In fact, we reported a giant tunneling magnetoresistance signal of the order of 3,200 computationally. Whether that is realizable experimentally or not is still yet to be found. I'm still eagerly waiting an experimentalist to write to me to say, no, this is not true, or yes, it is true. We also demonstrated the control of magnetization. You could see that we can basically apply spin transfer torque and use it to switch magnetization in the forward and in the reverse direction. All right. This is my first published paper at UKZN. It demonstrated the whole concept of chiral anomaly in spin density. You see at ground state, spin up and spin down conducting channels behave differently. If you look at the charge density, when resolved into spin channels, they tend to look alike if you don't look at it carefully. But when you do a one-to-one mapping, you start seeing different conducting channels. For example, you could see these distorted square-like regions here and this oval-like regions there. And the Fermi surface topology then looks like that. Okay. This work is an ongoing work on defect fingerprinting. Part of it was published last year, where we demonstrated the exploitation of defect identification and characterization for use in process chemistry industries. In this case, in catalysis for the catalytic dehydrogenation of propane to propene. But in principle, what we are able to do is to computationally track the signature of defects on a surface of a material. So for example, where you see the orange or the yellow color tend to denote the concentration of the defect signature on this particular material. In this case, this is my dopant on a surface, on an orthogonal surface, but this surface you can see has hexagonal symmetry. So what you see there in the yellow bit are your spin density map, which this allows us to give or to obtain the spin density map. So if you're interested in some hypothetical material and you want to see how the electron spin is distributed on your surface, we can compute it. So there shows you a quantum dot on some hexagonal, on some surface of intrinsic hexagonal symmetry. All right, so technically we can compute the point contact Andreev reflection spectroscopy, and that spectroscopy technique is a technique that allows for the ballistic conductance of the interface between some surface of a conductor and another material to be established. Basically, we track the signature of the first differential coefficient of the current with respect to the applied bias. Another area where I believe that collaboration with NITheP or NITheCS colleagues could help my work to be fruitful is the prediction of the local structure of amorphous materials. For example, here is work that I've calculated where we compute the oxygen bonding distances with species and the metal non-oxygen bonding species. I'm sure you know that an amorphous material has no intrinsic local order in its structure. Now, because of that intrinsic indeterminacy, experimental methods typically try to map the intrinsic structure factor, whether static structure factor or dynamic structure factor. But that still needs to be benchmarked against as prepared materials. Now, what I'm proposing and what I'm putting on offer is that with the computational tools we have at the UKZN, we can save you time, research time, beam time, by using machine learning techniques to develop evolutionary algorithms that allow us to benchmark whatever we calculate ab initio to what machine learning allows us to do, so that you'll know whether your experiment is even worth pursuing or not. All right, so here are where I think, here on this page, is a summary of where I believe that our emerging paradigms in quantum computing could benefit our emerging interest in the paradigm of quantum computing and machine learning can benefit the quantum computing community in terms of quantum optimal control, information processing, process tomography. Basically, we can do a computational study of the time evolution of this Lindblad equation. We can write Python modules to do this. And then this is where I want to conclude. You would imagine then that my personal take on all of this is that, quite frankly, drawing inspiration from Richard Feynman, who's famed to have written this piece in his chalkboard shortly after his death. It was reported that this is what he wrote in his class. And if you read it, it says, "What I cannot create, I do not understand. But my own is that what I cannot compute, I do not understand." With that, a personal note, I thank you for listening. Thank you very much, Chair. Over to you, please.
Yeah, Aniekan, thank you very much for a very interesting and detailed talk with a little philosophical underpinning towards the end. That was really very nice. I will now ask Ilya to please guide us through the question session, because I see there are a few questions in the Q&A facility.
Yes, okay. In fact, it's a one question, kind of like it's a two-part question by one of the listeners, and the listener is asking, thanks for very nice talk. You have mentioned at one point that the quantum near field electrodynamics that you are using for the enhancement. Can you please tell us more about this? And thanks in advance. And the second part is, and how to use it exact for enhancement.
Okay, Thank you very much for the questions. First of all, what I showed you there is the field enhancement around the condensed matter system. I am not using the field to enhance. No, that's not the case. What we are doing is we compute the global ground state of our condensed matter system, in this case, graphene or tantalum arsenide, as the case may be, and then apply a time-varying electromagnetic field and allow our global ground state density to evolve with time by solving that Schrödinger equation, that modified Schrödinger equation I shared with you. So what you then see is an enhancement of the applied field in the region surrounding the nuclei. So you are misunderstanding what I told you. I am representing an enhancement of the local field around the nuclei of our condensed matter system. All right, thank you for the...
Okay. And sorry, can I ask a question?
Please, go ahead.
Yeah, on some stage, kind of when you start kind of from the kind of conventional condensed matter stuff, moving a little bit to the more quantum information processing stuff, you mentioned that you are proposing the model of the magnetic qubit. Can you please go back to that slide?
Yeah, sure.
Mm-hmm. Yeah, and the question would be, okay, so the question would be very simple. It's like, so kind of to find, a system which have two distinct levels is usually, and that's, I think, what you are proposing. Yes, so kind of like you find the system which have two levels, and kind of is usually not a difficult task. I mean, there are a lot of candidates for the qubits, but do you have any idea about the typical coherence times, controllability of these states, ability to create, how it's called, the linear combinations of these states, so that you can create, I don't know, some arbitrary combinations, and maybe, even coupling these two magnetic qubits to each other in order to create two qubits or more qubits gates. Okay, thank you.
All right, thanks a lot for that interesting forward-looking question. In principle, no, I have not investigated that, but from a purely condensed matter theory perspective, you could see that the two states that represent the qubit are stable. Stable with respect to applied external perturbing field. So I'm assuming that they'll be reasonably stable, but in terms of looking at their coherence times, it's something that can be investigated. I would be interested in finding out how long the coherence time would be. But of course, you would imagine that I would need a lot of collaborative kind of engagement in that area, because traditionally it's not what I do routinely. Don't know if that answered your question, but
it's answered my question. Thank you.
Right.
Yeah, then Aniekan, it doesn't seem that there are any more urgent questions. Then
there is, sorry, there is a hand. Yeah. Let's ask Camille to ask questions.
Okay. Let me give then the right to.
I already done it.
Already done it. Okay, perfect. And Camille, please go ahead.
Camille, you are muted.
Sorry.
Camille.
You're still muted, Camille.
Hello. Yes, can you hear me now?
Yes.
Yes.
Yeah, sorry. I don't know what happened exactly. Yeah. Sorry for that. Yeah. So thank you for this overview. In fact, it's more like a comment than a question. And so, yeah, maybe just to put it in the context. So I am interested in some of us at UKZN are interested in quantum thermodynamics, And so, like yeah, so the usual or at least the initial steps is to consider like a very simple system, for instance, a two-level system, and to try to see if quantum properties such as coherence, quantum coherence, or entanglement can be used to do more than classical thermodynamics. But there's strong evidence that two simple systems like that are not rich enough to have so interesting properties. And so there are several papers now coming up suggesting that if you want to somehow to do better than classical thermodynamics, or if you want to get interesting quantum properties, you need more complicated system, meaning like spin chain or many body interaction, or even dissipation, many body system dissipated, and things like that. And so the problem is that when you start to study such problem, you very quickly realize that the full analytical solution is impossible. So you have to, the numerical tools become very compulsory. Without that, you can't do anything. And so all those papers now strongly relies on the numerics. So I mean, I don't have like right now exactly a detailed setup and system, but what I wanted to say that I mean, all this kind of work that you are able to do, I think, can be very useful for quantum thermodynamics and also quantum computation. Also, because analytically we are very, very limited. And all relevant system now, and you need numerics. So yes, that was my comment.
All right, thank you very much for that comment, and I fully agree with you. For me, we are living in a world of possibilities. So to me, I would say, to see what is doable, send me an email. Let's do it. I mean, if it is worth doing, let's do it.
Yeah. Okay. All right. Yes. I'll do that. Yeah. No problem.
Okay.
And just I mean, another comment. What people looks much simpler than what you're doing. So I think it shouldn't be a big problem for you.
Okay.
All right. Thanks a lot. I don't know whether it's appropriate for me to comment about the complexity or otherwise of what I do, but what I can tell you is that nowadays, you don't need to go into complex systems to get insight into the physics of your system. I think the challenge is to define the problem into a form that can be solvable. Otherwise, if the problem is intractable, then you have to find a numerical recipe for reducing the theoretical problem to a computational problem. Otherwise, I'm afraid there's nothing that can be done.
Okay, then Aniekan, since I'm just looking at the time and I see that our participants are starting to go home, or maybe they're already at home. So Aniekan, thank you very much for the nice talk. I was very pleased that you kickstarted some very interesting discussions that we will be very keen to follow up on. And see if it leads to some new collaborations. That will be really a very positive outcome of this this colloquium. So Aniekan, sorry, I forgot at the beginning to mention that you are one of the last associates that joined NITheP before it became NITheCS. Yeah, so congratulations for that as well, and welcome to the bigger NITheCS family as well. Yeah, so thank you very much, everyone. I wish you a good evening, and I'm looking forward to see you here again in Zoom next Monday, where we'll have another very exciting, a little bit more historical for a change lecture. Yeah. So thank you very much. Have a good evening and all the best. Yeah.
Thank you very much, Francesco. Thank you, Ilya. Cheers. Goodbye.
Thank you, Nick, and
Thank
bye.
you. Bye.